Okay, here we are, Chapter 8. This is Screws, Fasteners, and Non-Permanent Joints. And here's some definition of terms. We have pitch. Pitch right here. I'm going to disconnect the keyboard for a second. Here we go, pitch. Whoa! Bear with me. Pitch. That's this right here. Let me erase that. Right there. That's the distance between adjacent threads. That's different than the lead. The lead, perhaps unbeknownst to you, you could have multi-threaded fasteners or power screws. And the lead is the axial distance one thread travels per revolution. So down here we have single threads, double threads, and triple threads. You can get more information here from Wikipedia, but we're not locked into a single thread device. We could have actually something that has two threads on the same screw. Major diameter, minor diameter, pitch diameter. These are all defined here. Right there. That's these three. And the thread angle, 2 alpha, is the total angle created by adjacent threads. I believe this one is a figure out of the book. So, figure from the book. So, obviously you want to check out those definitions, but graphically they're shown there. There's thread designations. There's English and metric. There's UN, UNR for greater root radius. And the reason why you'd want a greater root radius is to eliminate a notch condition for fatigue failure. Same thing for metric. They have the same stuff here. Then they have quality. UNC, UNF, and UNEF. I've only actually seen these two. I've never actually seen a UNEF extra fine thread, but if you ever need one, it'd probably be for some extremely precision placement of something like a laser optical system. So this one is not particularly typical. Table 8.1 and 8.2, they have, this is a really useful table. Here, I'm going to pull this up here. Oh, that's my arm. Table 8.1 and 8.2, let me scroll back a little bit here. Over here, we have metric. Over here, we have English. And down here, this is a particularly figure 8.3, where my finger is going back and forth right now. This is now a conglomeration of stuff that can be a little bit confusing. These two tables are for general threads, like screws. This right here is for power screws. Power screws are not fasteners. Power screws deliver, as their name implies, either power or position. And they are guided by either square threads or Acme threads. So these two tables here are for threaded fasteners, and threaded screws, threaded devices, except for power screws, which is in table 8.3. Let's get back to the lecture notes here. So I would say figure 8.3 is for power screws. And maybe some of you have seen power screws in the basement of an older home here in Cleveland, holding up one of the joists, one of the structural joists. And you'll notice that those things generally have either a square, let's get back to it. They usually have a square thread if it's for a structural thing, and possibly an Acme thread. But the ones in your basement will almost definitely not be an Acme thread. Okay. Here's table 8.1. One of the things I'd like to stress here is the tensile stress area. Whoop. Stress this. This is used in stress calculations. That's basically this column right here is one of the more important columns. I can do a better arrow than that. There we go. There we go. No, that wasn't much better. I'm still learning. Maybe my handwriting is just really bad. Anyhow, the tensile stress area, A sub t, we're going to use that later in the chapter. So obviously you want to be able to determine whether or not your screw is going to fail or not, or how to design it. So that's based on size. And then same thing here, tensile stress area. You want to make sure you don't put too much tension on your threaded device. Again, table 8.1 and 8.2, although they're presented here at the beginning of chapter 8, have nothing to do with power screws. So table 8.1 and 8.2 don't apply to power screws. I'm going to change one of my settings here. Bear with me. Ignore touch input when I'm using my pen. Done. Okay. Now we finally get the power screw threads in chapter 8. Like I said, power screws. These are used for either positioning, whoops, or I would say force. They are not for fastening. Power screws are either to position something or to force something to where you want it to go. So it's the transmit power position. Like I said before, there's either a square or Acme option, and those are the only two options. However, within the square or Acme, you could have multiple threads. So you have square or Acme with single or multiple threads. Threads. And here's a really important table. In my opinion, it's kind of hidden. And I'm going to go back to the presenter view here and turn the page. Right up here. Standard sizes for autofocus. There we go. Right here, table 8.3. These are standard sizes for, the actual table says preferred pitches for Acme threads. But these are some standard sizes for power screws. Here's a picture of what a power screw might look like. Same thing over here. The book goes into this detailed derivation of free body diagram, and then all these formulas, which are mostly incomplete and confusing. Unfortunately, when they have T sub r, this equation right here, equation 8.1, is incorrect, because the actual torque to raise includes another factor. Same thing as torque to lower, 8.2. This formula is incorrect, even by the book's definitions, because of what we have over on, let's see where it is, collar, right here. Because of equation 8.6, if you have collar friction, you have to add that into 8.1 and 8.2. So if you read through this section, the actual torque to raise, T sub r, a power screw, includes equation 8.6. Now they include that in the verbal description here, but they don't actually include it in the formula. So let's try to navigate through that. So power screw equations, torque to raise, torque to lower, a couple things. These equations, again, are incomplete, which is annoying. And L, this right here, this is not a 1. This is a common mistake I get on quizzes, exams, whatever. This is an L, not a 1. And L stands for the lead. Now, let's take a step back for a second. The definition of lead and pitch. Where is that? Okay. So pitch, right here, is the distance between adjacent threads. However, you could have a double thread, let me get rid of that, or a triple thread, in which case the lead, in this case, the lead equals twice the pitch. And in this case, the lead equals 3 times the pitch, because there's 3 threads. In the previous case, there's 2 threads. All right? So these formulas, okay, so to my point, we're working with lead here, not pitch. In the torque to raise, this is torque to raise, T sub r, and torque to lower, a power screw. There's a couple things to note here. If the lowering torque is negative, the load will lower itself by causing the screw to spin without any external effort. So this is dangerous. This is potentially dangerous. Whoops. I love the eraser on the Surface Pen. So this is potentially dangerous. If you have a power screw and it can self-lower, that's not necessarily a good thing, obviously. If the lowering torque is positive, the screw is called self-locking. And that's generally what you want for like a structural element, but not necessarily a positioning element. So the self-locking condition is, as stated in the book, pi f d sub m is greater than L. Again, this is an L. That's an L. F is the coefficient of friction. D sub m is the minor diameter. L is the lead. This equation got all screwed up. This one is should actually read, let's see here, I'm reading out of the book now, L over pi L over pi d at d sub m equals tangent lambda. So this one did not make the transition well from a previous version of PowerPoint. But that would be right above equation 8.3 in the book, if you want to see this formula right here. However, the self-locking condition is that. So here's the self-locking condition. The coefficient of friction is greater than tangent of lambda. Efficiency, we're not really interested in this. unless you have a high-speed positioning device and you're trying to size the motor. And I'll make that. I just want to point out here that we're throwing out terms here. Obviously, you understand in this equation. I just want to backtrack here a little bit. F is the coefficient of friction. And what is lambda? Well, if you read the chapter, that's the thread angle. Whoa! And for that, we can go actually back to this, and you can see lambda is identified right here in figure 8.6. Okay, Acme power screw equations. These are not properly presented in the book. They give 8.5. But that's the torque to raise, T sub r, for an Acme power screw. But they don't actually list the torque to lower. Sorry, I'm rehydrating here in the background. This is not in the book. They kind of give you some hints how to do it, but hey, follow the same trends as 8.5, but this is actually not in the book, but used in some of the problems, and also particularly useful in lowering an Acme thread. So you're still responsible for being able to apply the torque to lower for an Acme thread, and secant alpha is the let me see if I can find that here. Let's zoom in. Zooming in on the book here. Two alpha. This is an Acme thread. Shown in the left-hand side. 2 alpha is the angle created by two adjacent threads. So alpha would be 1/2 that angle. That's down in figure 8.7 right here. So this angle created here is 2 alpha. So in that equation that we're looking at right here, alpha, that's 1/2 of the angle created by two adjacent threads. L, these are still L's. These are L's, not 1's. And F is the coefficient of friction. D sub m is the minor diameter. Now here's the part that is sort of missing from the book. Collar friction. So when you're talking about torque to raise and torque to lower a power screw, the collar actually has something to play in that. And here's the collar friction. It is the force being exerted, that the load that you're trying to carry. F sub c is the collar friction. D sub c is the average diameter of the collar, divided by 2 is the collar friction. Now this is not shown in the book right here, that these are the actual torques to raise and torques to lower a power screw. So I've annotated these equations, 8, 6, A and B. These are not in the book right here. It's written about in the book, but it's explained in the book, but it's not explicitly put in the book except when you get to an example problem. And so if I ask you, what's the torque to raise, and there's a collar involved, then you have to include the collar term in the torque to raise. Likewise in the torque to lower. So this right here is torque to raise, and this is torque to lower. Now this has a bearing on self-locking, that the collar can actually cause the power screw to be self-locking even if T sub L is less than 1. So if this is less than, or actually less than 0. So if T sub L is less than 0, it would normally be self-disassembling. However, if you have some collar friction, that can make it self-locking again. And you have to check for that, or design it for that. Okay, here's another vaguely defined part of Chapter 8, is the thread deformation in the screw nut combination. Thread deformation in screw nut combination. Basically what's happening here is that as you load the power screw and the nut, the power screw is in compression, which causes it to shorten, and the nut is in tension, which causes it to lengthen, and consequently the threads basically do not share the load equally. And the first thread, this is the most important part, which I have underlined, carries 38% of the load. And that's essentially your failure criteria. That's the most load that any thread carries, because the second thread carries 25%, the third thread carries 18%, and basically by the time you get to the seventh thread, it's free of load. So the book does this again in example problems, but they don't properly explain it in the text. So I would say here that the text uses what I'm saying here in the examples and the problems, but it doesn't really explain it well. I don't think that's well. Here we go. Well, as a matter of fact, I'm flipping through the book here, and looking at the book, it's explained right here on page 411. Screw thread form is complicated form of analysis, blah blah blah. And here they explain where, here's the 0.38. So if you're looking for, in the example problems, where does this number 0.38 suddenly pop out from? It's from this text right here on page 411. And it basically negates all the other formulas that are over here. It essentially makes all these useless. So let's get to it, and I'll correct everything as we go along. So we have stresses in the power screws. Obviously, you want to make sure this thing doesn't fail. This one's correct. Maximum body shear stress, axial stress, and we're looking at something that's loaded here. You know, where are these actual stresses? Axial stress in the screw body. We don't really care about that. Bearing stress on the top of the threads, we definitely care about that, because that's a failure criteria. And they have this formula in the book, but that's actually not used in any of their example problems, because they use this thing right here, the 0.38 on the first thread. So what they do is they focus on all the example problems on the first thread. That's not explicitly put in the book as an equation. So I have added this part here. So this is a modified equation 810. It's corrected as it's stated here. So if you're looking for the bearing stress, and the bearing stress is the stress on this surface right here, the top surface or bottom surface, depending on which way you're rotating this thing. So, and that's definitely a failure criterion for these threaded devices. Again, bending stress at the root of the thread. This is at the root of the thread is a typical failure point for power screws and screws in general. And this is all the stuff that's in the book, blah, blah, blah. And it's incorrect, because what they do is they use the 0.38F again, and this is what they use. This is used in the example problems. And in the suggested problems. And that's basically the formula that you want to use. So this is a modified version of 811. Please make a note of it. Transverse shear stress at the root of the thread. Again, this one's okay. The combined stresses at the top of the root plane. Basically, there's several formulas in the textbook that are incomplete and missing. I think I've corrected them here. And the next slide will show kind of a summary of the book formula set and the corrected set of combined stresses at the thread root. And this is really where we want to examine if we're having a failure or not. The thread root is the location to be considered for failure analysis. So we're looking at combined stresses at the root plane. So combined stresses at the root plane. This is the book formula set, and it's incomplete and misleading. You have to read the text. To understand that this is not used in I hate to say it, these formulas are not used in their own example problems. And they're not used in the problems in the problem section of this chapter. Here's the corrected formulas, as far as I can tell. And I know it's a little bit small. Maybe I can. There it is. Boom. So we have the 0.38 up here, and we have a conditional statement here. If there's no torque being applied, or if the power screw is being raised or lowered, these are the various stresses that would be in there. And then you would use the von Mises stress to check for failure with a factor of safety. Okay, I'm going to reattach the keyboard here so I can take a brief pause. That'll be part one of the lecture. If I can get the keyboard back up, and we'll continue on after this.